Okay, first we'd like to thank you for being here, Dr. Hedengren, and giving us this audience. We'd also like to thank and acknowledge Dr. Larry Baxter and Mark Jensen for their expertise and helping us with this project and setting it up. We have a few objectives that we're going to talk about today. So the first one is going to be our process description, exactly what it is, gathering the data, what we did to get it, generating the transfer functions from that data, building the models, tuning the controllers, the system performance, and then what we think is the best storage strategy for control of this system. So the first part of this process, we have this bubbler here. So we have our gas comes in this way and it goes up through the bubbler. And this bubbler is a CO2 desublimation. And so essentially it's a single stage distillation column with the gas coming up this way and the liquid coming down, and then there's a plate in here. So the gas comes this way and the liquid bubbles, the gas bubbles up through the liquid. We have a gas analyzer, a pressure and temperature transducer hooked up to our pump, and then we have a refrigeration system also. So our goal is to control the concentration through variation and pressure, which we do through the gas flow, and then we vary the temperature through coolant flow. One of the things that's interesting about this is that pressure and temperature are coupled because of the ideal gas law, and they're on opposite sides. So you can see in order to desublimate, we have to be at minus 130 degrees Celsius on this side, and then we also want to increase our pressure, and so they're on opposite sides. So as you increase pressure, temperature also increases, so they're somewhat competing. And so we needed to design a simulate model to account for that, and so we wanted to compare a non-interacting to an interacting controller. And next we'll talk about how we actually gain data from this system.
So there are two options you have to get information to generate transfer functions when you build your simulate model. We thought about doing first principles, looking at the equations, ideal gas, and trying to relate temperature and pressure in that way. But because we have an actual unit that Colin has a lot of expertise in and can run actual experiments on, we decided to do doublet tests so that instead of predicting what's going to happen, we actually know what's happening inside the system. So there were two things that we did. For some of the processes, they were non-interacting, and for some of the processes, they were interacting. So we had integrating. There's an integrating process here with pressure as a function of the mass flow rate of gas coming in. And then there's non-integrating processes like concentration and pressure as a function of the coolant flow rate, or concentration as a function of the mass flow rate in. So there's different approaches to getting the transfer functions from non-integrating versus integrating processes. And so when we did the doublet test to measure what would happen to temperature as a function of the coolant flow rate, we were able to get a very good FOPDT fit in Excel, and then we could relate that to the concentration and the pressure, and similarly get an FOPDT model fit. We were able to get our transfer functions from that in a pretty straightforward way. But for our integrating process of pressure as a function of the mass flow rate of gas in, because that's an integrating process, we had to determine this graphically. So looking at the slope of the response based on our doublet tests, we're able to get the transfer function from that, but not through an Excel fit. So by using these methods, we're able to generate our transfer functions, which we implemented in our Simulink block diagram, which we can see here on this slide. Now this shows just the interacting control strategy here, which you can see in these transfer functions, which help us to account for the fact that these are interacting and that temperature and pressure are going to compete with each other, like Colin said. And so we implemented these transfer functions that we found from our doublet tests here, and then using the ratios of our process versus our disturbance transfer functions, we're able to get the ratios that should give us a theoretically perfect control, predicting what's going to happen to the coolant flow rate when you change the mass flow rate, and vice versa. And then by predicting what our transfer functions would be, we were able to generate predictions for our P and PI controllers, and then tune those to get the best performance from the system.
Mm-hmm. So you'll notice we have our controller tuning parameters on the right, and they're rather large values. So we have a value of 10,000 for our P-only controller, which makes sense for this process because as you see a large numerical value change in set point for mass flow rate, you only see a small response in pressure. And similarly for the PI controller, we have -1 million as our p-value, And that's because for a large change in RPMs in the pump, you see a very small temperature and those concentration change. And you also notice that it is a negative 1 million because as you increase the RPMs of the pump, it's going to decrease the temperature. We also did some stability analysis by changing the controller parameters in Simulink to try to determine where our controllers would go unstable. And we found that there was actually a really broad range of stability, and that can be found in our written report. So these are kind of the results of our comparison between interacting and non-interacting control. The blue line is our interacting control, and the green is our non-interacting. And you can see that the kind of the amplitude there of each of the control strategies. For the interacting control, it has a little bit of overshoot, and that can be kind of decreased by changing the gain of the K value in those transfer functions in the interacting control. But it is a lot smaller of a disturbance to the system than if we use a non-interacting control. So, and also you can see that in the non-interacting control, it doesn't actually go back up to the same set point value that the interacting control did. And on that top graph is pressure. At the bottom, concentration plot. It's a little bit difficult to see, but the blue line reaches the set point a little bit faster than the green line, so it does have a little bit better performance. But you can see that although there's a little bit of offset, it does a pretty good job of tracking the set point, whether it's interacting or non-interacting. So in conclusion, we would recommend using the interacting control because we don't see as large of a disturbance when we have set point changes.